any inertial particle can really represent itself as being stationary, meaning its world line being vertical along the t-axis. But it cannot be along here without special relativity. You don't need special relativity for that. So there's clearly something about time more here than space. We see there's something special about the time axis in this diagram. It's not the same as the space axis. Now, I'm going to do something that's a leap of imagination. All right, and I'm going to say, what happens if I do something funny, a little bit strange to time? What would happen if I did something a little strange to time? And we'll talk about this more afterwards. I warped it in some way. Okay? Again, everything that I say about time is going to have to be in the context of like space-time. The space, without the space thing, nothing's going to happen. But we're warping the time. And I'm going to try to define a type of warping which will cause a curved world line to straighten out and a straight world line to curve. Naively, you might imagine if there's a curved world line, right, I don't care if it's like this or like that, I'm not going to pay attention to the axes and so on. If I have a curved world line and I kind of bent the time axis, it'll kind of pull this thing straight. And if something is straight, that's actually not the correct image. All right, for various reasons. One reason being that if you're curving it into the x, and you're mixing space and time, and it gets, whatever, it's not clear what that means. We'll see that there's another way to deform time within the context of space-time that will actually do this trick. But at this moment, we're just saying heuristically, what would happen? And if it turns out to be something nice, let's see if we can build a rigorous mathematical theory that does this. Okay? So now, a region of space-time, which is where the time is just ordinary, it's not warped. All right, there's particles, there's accelerated particles, inertial particles moving in all kinds of directions all over the place. Suddenly, for some reason, somehow we manage to do this strange thing to time. Okay, what's going to happen? What will you suddenly see?
Time slows down.
Pardon me?
Time slows down. That's the idea.
I didn't say how I'm warping it.
Yeah,
Okay, correct?
okay.
So what would you see happening? Some change? Is there a change as a result?
You mean in the space-time?
Right, I'm looking at a physics, at a location in the universe somewhere, where there were all kinds of particles running back and forth, doing all kinds of things, kind of moving in strange accelerations and in magnetic fields, and there were inertial particles, all kinds of things. And then suddenly I did this funny thing to time, to space-time. What, if it's the kind of thing that I just spoke about before, what will happen?
Nothing.
Good mix. Yeah. Stationary particles would change into accelerating particles.
Okay, right,
You can
because?
separate them out.
Anybody agree, disagree?
Just the element cycle.
Okay, what will you see? Pardon me?
See the particle act differently.
How will they act differently? As you said,
Vectors.
those particles that had an acceleration might end up having a world line straight. Some particles that had a straight world line might end up having a curved world line. Now, if there's a certain measure, if you warp the time in a certain specific degree, then you will have uncurved world lines by a specific amount. So a world line which was curved exactly that amount will end up being straight and therefore inertial. Right? Particles that had more or less or whatever, it'll be different. But certain particles that were accelerated will suddenly be inertial. Certain particles that were inertial will be accelerated. Now, how would you characterize the action of this strange phenomenon? Somebody's observing this. What will they find, in addition to just the fact that some particles are accelerated and some not, and they change from inertial to accelerated? What other very important feature of this will be observed? Okay. Sorry? Yes. Okay, that's part of it. Somebody else doesn't?
The existence of a new force. You didn't know that.
Okay, right. You see that there's some kind of force. There's accelerations over here. How would you characterize, what is very unusual about this force? In other words, you open your eyes, you see everything is different. Well, Big deal. So somebody, you know, exerted a force here, right? Somebody turned on a big generator, and there's this huge, whatever, nuclear, electromagnetic, something force causing all this stuff to happen.
It doesn't have to do with mass,
Go on.
because it's the same for all particles.
Correct. How do you know?
I don't know
The
about
definition
mass,
of inertia.
trajectories in space.
What I said was that it has to do with the curvature. If you're uncurving things or curving things, it has nothing whatsoever to do with the mass. It has to do with how much acceleration you have. Now, somebody observing this would say this is a very weird phenomenon. A phenomenon where particles are accelerating with the same amount suddenly, irrespective of their mass. Who ever heard of such a strange thing? Is this physical? Could it be that there's a force that accelerates all particles, irrespective of their mass, adds acceleration, even if they were moving with different velocities in different directions, right? It suddenly gives them all the same acceleration. Whoever, is that physical, or is that like something too odd for physics? Gravitation. Okay? That's exactly the unique feature of gravity. So immediately what we see is, if we could successfully create a warped time, space-time theory, we would have a theory of gravity. Now that is certainly a motivation to try to start from scratch and do this all rigorously. Okay? So now, a region of space-time, which is where the time is just ordinary, it's not warped. All right, there's particles, there's accelerated particles, inertial particles moving in all kinds of directions all over the place. Suddenly, for some reason, somehow we manage to do this strange thing to time. Okay, what's going to happen? What will you suddenly see?
Time slows down.
Pardon me?
Time slows down. That's the idea.
I didn't say how I'm warping it.
Yeah,
Okay, correct?
okay.
If you know, if you're aware, there's a difference if you're aware that this happened to time or if you didn't. Let's say if you weren't aware that anybody did anything to time. You close your eyes, somebody did this, you open your eyes, what will you notice different? You're still in the same place that you were before, but you're in a rocket and you're in empty intergalactic space where there's nothing around and things were moving inertially, but maybe there were some magnetic fields and there were some particles. You don't know what was out there, but there were accelerated particles relative to you. You didn't feel any inertial forces, so you assumed that you're inertial. And you saw some particles moving inertially and some accelerated, and now you open your eyes, what will you suddenly see? Now, imagine something wild, something crazy, that would warp the time in this region of space. Okay, I'm going to warp it in such a way that this world line will uncurve. Now, the first imagination you have is maybe I'm going to curve this timeline and uncurve this as a result. But it doesn't have to be that. It's just I'm going to warp the time in some way that this is going to uncurve and become a straight line. Now, of course, it's a straight line in this warped time, and therefore it's not going to be exactly a straight line. It's going to be the straightest possible line in a warped time. So one can imagine that you have the language of curvature here. There's a curved line. You're doing something to warp the time. That warping will cause an uncurving of this world line, and therefore maybe we can call that warping curvature. But we'll get to that later on. And again, this is just a naive and wild proposal. It turns out, of course, that using differential geometry, one can do this rigorously. Now, what would happen to all these particles? You have particles accelerating in different ways, moving with inertial speeds in this region of warp time. What is going to happen to them when you suddenly warp it? As a result of the warping, the inertial particles which have straight world line are suddenly going to have curved world lines. Some of the particles which have curved world lines are going to uncurve and have straight world lines. Okay? Now, if you warp this time in a certain way, then there's going to be some specific set of particles with a specific type of acceleration somehow related to this. Right? They have some kind of an acceleration which is a world line curvature. You have an intuition that there's going to be some characteristic of this warping which is going to map to this value. the amount of curvature here will correspond to the degree of the warping of time necessary to straighten it. So to whatever, let's say you warp it by an amount, whatever it is, one particular set of world lines will uncurve and become geodesic. And all the others won't, because it's not the right kind of warping. So what you'll see is certain particles that are allegedly accelerating will suddenly feel allegedly inertial. And some of the particles which were inertial, or all of the particles which were inertial, will suddenly start accelerating. The amount of curvature here will correspond to the degree of the warping of time necessary to straighten it. If you warp this time in a certain way, then there's going to be some specific set of particles with a specific type of acceleration somehow related to this. Right? They have some kind of an acceleration which is a world line curvature. You have an intuition that there's going to be some characteristic of this warping which is going to map to this value. As a result of the warping, the inertial particles which have straight world line are suddenly going to have curved world lines. Now, of course, it's a straight line in this warped time, so the more general term, of course, would be geodesic. You can imagine that you have the language of curvature here. There's a curved line. You're doing something to warp the time. That warping will cause an uncurving of this world line, and therefore maybe we can call that warping curvature. But we'll get to that later on. And again, this is just a naive and wild proposal. It turns out, of course, that using differential geometry, one can do this rigorously. Now, one of the interesting features of this is that it's, of course, independent of the characteristics of the particle. If the reason for the acceleration is this warping of the time, and the warping of the time has nothing to do with the particles, it's the time itself, then clearly all particles will be equally affected. Okay? So in other words, all inertial particles will suddenly accelerate in the same way. Now, what I do is I can simply pose it to any kind of student who studied mechanics and ask them, is that at all possible? Does it make any sense that you'll have inertial particles, and as a result of some kind of field, suddenly they all accelerate, and they all accelerate in the same way, irrespective of their characteristics? Is that at all physically intuitive? And the answer, of course, comes up very quickly. Yes, that's gravity. Now, one of the interesting features of this is that it's, of course, independent of the characteristics of the particle. If the reason for the acceleration is this warping of the time, and the warping of the time has nothing to do with the particles, it's the time itself, then clearly all particles will be equally affected. Okay? So in other words, all inertial particles will suddenly accelerate in the same way. Now, what I do is I can simply pose it to any kind of student who's studied mechanics and ask them, is that at all possible? Does it make any sense that you'll have inertial particles, and as a result of some kind of field, suddenly they all accelerate, and they all accelerate in the same way, irrespective of their characteristics? Is that at all physically intuitive? And the answer, of course, comes up very quickly. Yes, that's gravity. So gravity has exactly that feature, which is the equivalence principle, that all masses accelerate in the same way. When they come into a certain region of space, they all accelerate. Now, depending on their initial conditions, their direction and speed, their acceleration is added on to the velocity and takes them in a different trajectory and so on. But at any given point in space where there's a gravitational field, there's a unique acceleration pointing in some direction, and it doesn't really matter how the particles are moving with whatever speed, they all have this acceleration at this point in space. All right, so it's very clear immediately that a model of time warping will produce gravity. Now, of course, one would have to adjust all the parameters and so on to get the equations. But the equivalence principle maps directly onto this picture. So, a straight line in space, y is equal to mx plus b, the xy axis. A straight line in space-time, as we spoke about, our inertial particle world lines have straight lines. X is equal to vt. V would be the speed, or the inverse of the speed, and it's the slope of the line in the tx. All right, so this slope over here is the inverse of the speed. And so vt, the speed times t plus b, that's a linear relationship between the two. All right, so this is the equation of a straight line. Now, imagine a bunch of particles in some region of space during some particular time. They all have different accelerations. They all have different world lines with different curvatures. Okay? So now, let's do something crazy, right? We're going to try something out in our imagination. And what we're going to do is, we're going to try to imagine that we could warp that time axis. Weird. It's not clear that we can do that if it has any meaning. All right, so it's very clear immediately that a model of time warping will produce gravity. Now, of course, one would have to adjust all the parameters and so on to get the equations. But the equivalence principle maps directly onto this picture. Now that we have an understanding that we're talking about a theory of gravity, let's start from scratch with gravity. Okay? A field in the space around this spherically symmetric object, and it's an acceleration field given by this. We can go one step further and talk, instead about the acceleration, we can now talk about the world line curvature. And we can say, what is gravity? It's a theory of world line curvature. Outside a spherically symmetric mass, you have a field of world line curvature, and any particle crossing a particular point, no matter what their initial conditions, no matter their mass, has the same world line curvature as a result of this field. So we can now recast this, instead of calling it acceleration, I can maybe give it some kind of a symbol, world line curvature. I'll call it this, gamma. All right? So I can now say gamma equals gm over r squared. This is my world line curvature field. Okay? And again, this is totally Newtonian. I didn't talk about anything that is not purely Newtonian and Newtonian gravity. Now we can take it one step further, as I said before, about warping time. And now we're talking already about a differential geometry theory. Okay? And we know that there'll be some characteristic in that warped time which will map onto this. In other words, to the degree that this world line is curved, we're going to warp or curve the timeline in such a way that it straightens this out and makes it geodesic. So instead of this being curved, the geodesics of that warped time or space-time are going to have some kind of a geodesic curvature. Now, of course, a geodesic by definition is the straightest possible line, so it doesn't make sense to call it curvature, but there is some kind of a concept of geodesic curvature. If you took, for example, a curved surface and you drew a geodesic on it, the straightest possible line, if you looked from outside the surface, you could get some kind of curvature. If you're talking about intrinsically, then of course you wouldn't really be able to define that curvature. So this is a not really well-defined type of curvature, but you know that there will be something in that theory, in the differential geometry description of that theory, which will have something to do with the geodesics and the curvature of the geodesics in this warped time or space-time, and that will map to the acceleration, which is the world line curvature. All right? So we already have now a different theory. We can look at the same equation and say, at least in those situations where Newtonian gravity is correct, we will expect that whatever this higher level theory built on differential geometry and so on, whatever it is, it will map and reduce eventually down to this equation, something very much like this equation. Okay? Let me just stop here for an instant and just add if there's any questions about what I'm doing. Okay? Any questions of why I'm doing it or what I'm doing? All clear? All right. So now one can ask, what might be the field theory of such, right? What might be a field theory for this? So we have a differential equation that is a field equation for the acceleration.